In the previous lecture, we introduced the concept of boundary layer. The boundary layer is the region near the wall in which viscous effects are important and because of which we see large gradients in velocity in the boundary layer region. Even if the Reynolds number of the flow is very high, we consider a small layer near the wall where viscous effects are important, or viscous effects and inertial effects are of similar magnitude. So, using boundary layer in the previous class, we saw that some of the physical phenomena such as the presence of non-zero drag on the submerged surfaces or on the bodies could not be explained by assuming potential flow for the cases where the Reynolds number is high and the flow is or the approximation of inviscid and potential flow is closely valid, or it's approximately valid there. So, we introduced the concept of boundary layer, and then we defined the thickness of this boundary layer region in different ways: boundary layer thickness, or what we call disturbance thickness, momentum thickness, and displacement thickness. Then we looked at the Navier-Stokes equation for an incompressible steady two-dimensional flow over a boundary layer, and simplified the Navier-Stokes equation so that we can find or the solution of these equations to find the velocity and flow profile in the boundary layer. Now, what we are going to discuss today is the momentum integral equation in the boundary layer. So, we will consider the boundary layer region and apply macroscopic mass and momentum balances so that we get a equation, and that equation can be used to find the macroscopic properties. So, the equations that we wrote in the previous class, when we solve these equations, we will be able to find the differential or what would be that would be differential analysis, because we will be able to find the velocity at every point. However, the mathematics for the solution of such equations is slightly involved. So, we will not do that in this course, but what we will do is do the macroscopic balance, and that of course will give us macroscopic properties. For example, we will be able to find out when we solve this equation, we will be able to find out thickness of the boundary layer and the shear stress. Okay. So, we can find the macroscopic features, for example, boundary layer thickness and shear stress or skin friction coefficient. Now, this will require that we need the velocity profile in the flow. So, we will need to either we will need to make an assumption about the velocity profile, or we will need to know the velocity profile in the flow in order to be able to apply this equation. Okay. Because when we will do this analysis, we will not make any assumptions about if the flow is laminar or the flow is turbulent. So, this analysis will be valid for laminar as well as turbulent flow. Now, when we do differential analysis, the equations that we use can be valid for both, but we will need to be able to resolve all the features. For example, when we talk about velocity profile, 1/7th law of velocity profile for turbulent flow, that is not valid in the near wall region. So, the differential analysis that we could do accurately is for laminar boundary layers, but this analysis will be valid for laminar as well as turbulent boundary layers, and this will give us approximate values of boundary layer thickness and shear stress, and from shear stress integrated over the area we can find the drag force on any surface. Now, what we will need is, as an input, we will also need free stream velocity and pressure in the free stream. So, when we solve the flow in this outer region where the potential flow is valid, then we will be able to obtain what is u infinity and what is pressure distribution in this region. Now, remember that we said that dou p over dou y is approximately 0. So, the pressure in the outer region, we can use the pressure in the outer region as well as in the boundary layer at any cross section x. Now, there is another important feature that the velocity profiles in the boundary layer, they are self similar. So, if we write down the velocity profile in the form u by u infinity, where u infinity is the free stream velocity and u is the u will vary as a function of y, as you can see from here, that the velocity at the wall is 0 and then it reaches to u infinity at the boundary layer. So, this profile at any x, that will be self similar. So, that will be function of y, or in non-dimensional form y over delta, where delta is the film thickness. Now, u by infinity will be same at all x, but u will be a function of x. You can see from here this delta is not constant, delta is a function of x. So, the boundary layer profile that we talk about is self similar, it is called that u by u infinity is same at every x in terms of f function of y by delta. Okay. So, to start this analysis, we will again consider the flow to be steady, that means it is time independent, it is not transient, flow is incompressible, and we will consider a two dimensional flow in x and y coordinates. So, we will consider the Cartesian coordinate system, okay, and we will consider a small volume. So, we will consider a control volume A, B, C, D here as shown by the dotted line. Okay. So, this control volume is encompasses the fluid which is next to the wall. So, it starts from y is equal to 0 and goes on up to a region y is equal to capital Y. So, we consider here that the BC surface is parallel to this wall and AB is normal to the free stream direction of velocity, and then you have CD. The distance between A and D is dx. So, we can say that the coordinate at A is x and coordinate at D axial the x direction coordinate is x plus dx at point D. So, x and x plus dx, and the y is equal to 0 to y is equal to capital Y. Now, this is necessarily this need to be in the outer region, so that the control volume covers the boundary layer, or it is beyond the boundary layer surface. The velocity of course, in this region will be u infinity. Now, this u infinity can be a function of x or not, it will depend on what case we are looking at. So, we will take u infinity as a function of x. So, now what we will do, we will write down the macroscopic momentum balance on this control volume. So, let us remind ourselves the Reynolds transport theorem, where we have forces, the surface force and body force, and then dou by dou t of u rho dV, which is rate of change of momentum in the control volume and the momentum flux at the control surface. So, for control surface we have here A, B, C, D. So, we consider this force for x direction. Okay. So, the equation is for x direction, we have the subscripts as x, and for velocity component we have u here. Remember this v dot dA is a scalar quantity, right. Because the flow is Std. So, this term will be 0 and there is no body force present in this direction along the x direction. So, we will consider that this x direction is horizontal direction. So, f bx is equal to 0 or otherwise we can neglect the body forces. Now, so that will give us the momentum conservation equation will become that the sum of surface forces will on the control volume will be equal to integral u rho v dot dA over the control surface. So, we will evaluate each of these terms one by one. So, first we will evaluate the forces on this control volume f s x. So, on the surface of this control volume we will have 4 surfaces A B, B C, C D and D A. So, we will consider one by one. Now, if we look at surface A B, the force on this will be because of pressure along the x direction. So, if we consider that pressure at x is P and it will be compressive. So, it will act along positive x direction. Now, let us also assume that the width normal to screen is B. So, the area of this surface A B will be equal to B into integral 0 to capital Y dy, or we can write it simply as y, but we will later on come back to write it in this form. So, the force on surface A B will be P B dy. It may also have, it will have a shear stress, but the direction of the shear stress will be not be along the x direction, because the surface normal is along the x direction. Okay. So, the x direction force on another surface C D, that will be equal to now the force will act in this direction, the normal force. So, from Taylor series we can write the pressure here is P plus dP by dx. We can write it as dP by dx because P is not a function of y. So, we can write it as an normal derivative multiplied by dx. Remember that this distance is dx, and at A what we have coordinate is x, and at D x plus dx. So, pressure on the force due to pressure on surface C D is equal to minus, it will be acting in the negative x direction. So, that is why there is a minus sign here. Okay. So, minus P plus dP by dx into dx, and this multiplied by the area of surface, which is again B into y. Now, in the x direction on these two surfaces A B and C D, the forces will be because of normal forces. Now, if we look at surface B C, on the surface B C, the pressure will act in the y direction or in the negative y direction. So, we will not need to consider the pressure force on this surface, because what we are considering is F S x or force along the x direction. The other surface force is shear because of shear or viscous forces. Now, this is in the outer region where the flow is inviscid. So, when the flow is inviscid, the shear stress is 0. So, the force on surface B C is 0, or we can say F S x B C is equal to 0. Now, the force surface which is near the wall. So, on this again the force due to pressure will be normal to it. So, it will be along the y direction. So, what we will have is only the viscous force. So, let us say the wall shear stress which is a function of x. So, we can say just tau w will be multiplied by the area of this wall. So, the depth normal to the screen is b and this distance is dx. So, tau w b dx. So, we have written down forces on all four surfaces where force on BC surface is 0. Now, we can combine all these and find the final expression for f as x. So, when we add them together, the first on AB surface P into B into y, this is the force on surface A surface CD. So, P plus dP by dx into dx whole multiplied by By and minus tau w b dx. Remember this minus sign is because the shear stress on the fluid will be acting in the opposite direction of the flow. The flow happens along the positive x direction. So, PBY will cancel out because one is positive, another one is negative, and what we will end up with two terms minus dP by dx into dx b dy minus tau w b dx. Okay. So, we have obtained f as x and now we will go ahead and find out the fluxage on all the four surfaces of the control surface. Okay. So, that is the equation that we obtained for forces. We have taken b dx out of the bracket. Okay. Now, we will write down the fluxage on the surfaces. So, we can write down individually for all the four surfaces AB, BC, CD and DA. Now, we can see that on surface DA, there is no flow from this surface. So, this flow is going to be 0 and what we will have is let us start with surface AB. So, on the surface AB, we will have u rho v dot dA. Now, u is the velocity rho into v dot dA. So, on this surface the velocity is in this direction, or if you look at u. So, we will use the term u here because this region has u as well as u infinity. So, we can say that u which is a function of y and v dot dA, the normal to this, the area vector will be pointing as outward normal. So, as a result we will have a negative sign here and we can integrate it from 0 to y. So, u rho u b dy is the area dA of the surface if we take an element surface along the y direction. So, if we take a small strip of thickness dy. So, b dy and you integrate it from 0 to y. Now, similarly, we can write the flow rate on the surface BC. The same expression what we are going to write is because this is momentum flow and momentum flow because of if we write that this is momentum flow at AB, then at DC or CD we can write momentum flow at AB plus d by dx of momentum flow at AB into dx. We can write this from Taylor series. So, that is what we are going to do here. The momentum flow at AB is, the sign will be changed because here the outward normal and the velocity u both point in the same direction. So, the sign will be positive. So, the momentum flow will be 0 to y u rho u b dy. So, that is first term mf at AB plus d by dx of this. So, integral 0 to y u rho u b dy multiplied by dx. So, that is the momentum flow at surface BC. Now, we will consider the third surface, which is CD. We have already considered the surface CD. This should have been CD. Now, we consider the surface BC, because the flow here, it is not necessarily a streamline. So, flow which is going from here to here, there is some change in the flow rate, because when you consider say a boundary layer, and it will be clear if you look at that at the leading edge the velocity is uniform, but when you go inside the boundary layer or somewhere in the plate region, then there is a velocity gradient. So, the flow has to divert in this region. So, in the last class we also plotted the streamlines. The streamlines will be slightly diverted away from the region, and the distance between them will be increasing. So, the mass flow rate from AB to BC in this region in the boundary layer will decrease. So, you will have a net flow which is m dot BC. So, we will consider, we can write down that what is the flow here through surface BC is equal to u rho v dot dA. Now, rho v dot dA is the volumetric flow rate, and rho v dot dA is the mass flow rate from this surface. So, we can write this in terms of mass flow rate. So, rho v dot dA is mass flow rate through the surface BC, and u, because this region is in the outer region. So, the velocity here will be u infinity. So, u is equal to u infinity. Now, remember these coordinates are in terms of the boundary layer. So, if it is a flat plate, then this is along the flat plate. If it is a curved plate, then x is along the curved plate and the y will be normal to the curved plate. So, in any case, if the flow is not horizontal, then it is along the, or it is the u infinity is the velocity, free stream velocity, which is parallel to the plate direction. So, this is in any case it is u infinity. So, this is u infinity into m dot B C. So, we have obtained the fluxage or the momentum flows from AB or at the surface AB, BC and CD, and at the surface dA there is no flow either coming and going out, and there is no slip boundary condition there. So, this term is 0. Now, we can substitute these values in the momentum balance equation. So, the force on the right hand side and the momentum flux on the force on the left hand side and momentum flux on the right hand side, and we can substitute these values and try to simplify it. So, we see from here, so we can see that here we have a term b dx, and in this also we have b dx. So, we can divide throughout by b dx, because this term does not have b dx. So, this will be divided by b dx. So, when we write this and simplify, you will get minus within bracket dp by dx into y, where y is the distance between surfaces AD and BC, plus tau w, which is wall shear stress, is equal to d by dx integral 0 to y u rho u dy plus m dot BC by b dx into u infinity. Now, what we need to find is m dot BC. So, that can be found using the mass balance through this control volume. So, we can write down the mass balance equation, and in this mass balance equation, because the flow is steady, so this term is going to be 0, and we can consider the mass through all the surfaces here. Now, when we do that, we need to write the mass flow all the surfaces. So, at the surface A B, which is this one, we can write a mass flow is rho into u v dot d A, which will be b dy, okay, and we can integrate it from 0 to y. Similarly, on the surface C D, the mass flux will be like we did for the momentum flux, that the mass flux integral 0 to y rho u b dy plus d by dx into mass flow multiplied by dx. So, integral 0 to y rho u b dy multiplied by dx. So, the mass flow through B C is, let us say it is m dot B C, and there is no mass flow through surface D A. So, that will be 0. Now, when we combine these terms, these two terms will cancel out, and what will we get is m dot B C is equal to minus d by dx integral 0 to y rho u b dy. So, we can substitute this for m dot B C in this equation here. Okay. We can substitute it here. So, we have this equation which is a momentum balance equation, and in this we can substitute the value of m dot B C that we have just found out. So, when we substitute it, we get the following equation. Here we have written u into u. So, this has become u squared. So, we get the equation minus dp by dx into y plus tau w is equal to d by dx integral 0 to y u square rho dy minus u infinity comes here, and dx will cancel out, and this b will also be cancelled out. So, we will have inside the integral d by dx of integral 0 to y rho u dy. Okay. Now, we can write down the Bernoulli's theorem in the differential form of from potential flow. We can write down that in the outer region dp by dx, which is the pressure gradient along the x direction, plus rho u infinity d by dx of u infinity is equal to 0. Of course, in this the gravity is not considered. So, we will consider this to be horizontal surface. Now, from this we can substitute the value of dp by dx in terms of minus rho u infinity du infinity by dx. So, we will do that, and when we do that we can write this down equation as dp by dx. We can replace it by minus rho u infinity du infinity by dx, and in place of y we will write now it as 0 to capital Y dy y, because we have everywhere those integrals except in tau w, everywhere we have integrals from 0 to y. So, we will write this down in terms of integral 0 to capital Y, and see if we can simplify or combine these terms to get something which is familiar to us. There was this minus sign. So, we have changed the sign on the other side. So, that is why we have this sign here negative, and this sign has become positive. Okay. Everything else remains same. So, now we can divide by rho and rearrange it. So, we can write this equation in terms of rho. So, when we divide this term by rho, this will become tau w by rho, and the first term on the right hand side will be minus d by dx. This rho will cancel out. So, you will have integral 0 to y u squared dy, plus the second term will be u infinity d by dx integral 0 to y, rho will cancel out because we have divided the equation throughout by rho. So, integral 0 to y u dy plus this term will come on right hand side. So, rho will be divided, and it will become plus u infinity d by dx of u infinity integral 0 to y dy. Okay. So, let us look at this equation if we can do something here. So, this term, the first term, we can write down in a different form. So, if we take d by dx, or if we differentiate u infinity into integral 0 to y u dy. So, u infinity is also in general it can be a function of x. So, when we differentiate it by product, we will get differentiation of first function, which is u infinity. We can say this is first function and this is second function. So, du infinity by dx into integral 0 to y u dy, and then we will write u infinity into differentiation of second function. So, d by dx of integral 0 to y u dy. Now, we get this term is same as here. So, we can replace this term by d by dx of u infinity into integral 0 to y u dy minus du by du infinity by dx into integral 0 to y u dy. So, we can replace this term and see tau w upon rho is equal to, when we replace this term by the difference of these two terms. So, first term is d by dx of u infinity integral 0 to y u dy minus du infinity by dx integral 0 to y u dy, and then the remaining two terms here. So, which will be minus d by dx integral 0 to y u square dy plus u infinity du infinity by dx integral 0 to capital Y dy. Now, we can also consider this, we can bring in, because this is u infinity is constant with respect to y. So, we can even bring it inside the integral because it does not make a difference. Now, if we look at the two terms which are in green. So, both of them have differential d by dx, and when we combine these two terms, we will have u infinity into u minus u square dy. And if we remember the definition of displacement thickness, which was similar to where we had u infinity into u minus u infinity. So, we can combine these two terms and we can write them together. So, d by dx u infinity integral 0 to y u dy, and the other term d by dx of integral 0 to y u square dy. Similarly, we can write down this du infinity by dx into u infinity. So, this term comes here minus du infinity by dx integral 0 to y u dy, the remaining term. So, when we combine this, the first two terms, it will become tau w by rho is equal to d by dx of integral 0 to y u, because you have u squared here. So, one u can come outside the bracket, and within bracket you will have u infinity minus the remaining u into dy. Okay. And the other term will be du infinity by dx integral 0 to y u infinity minus u dy. Okay. Now, we have limit y here, but because when we go above y, u is equal to u infinity. So, both of these terms have u infinity minus u into them. So, the value of this integral from y to infinity will be 0, because u infinity minus u infinity will become 0. So, we can as well replace this limit with infinity. So, we have changed this limit to infinity. Now, we have tau w by rho is equal to dy dx integral 0 to infinity of u infinity minus u dy plus du infinity by dx integral 0 to infinity u infinity minus u into dy. Now, we can write down the definitions of displacement thickness and momentum thickness and compare these two. So, when we see momentum thickness integral 0 to infinity u by u infinity into 1 minus u infinity. So, if you write down or simplify it, it will be u I infinity into u infinity minus u divided by u infinity. So, this term is basically theta into u infinity squared. Similarly, the term here u infinity minus u dy integral 0 to infinity is basically delta star, which is displacement thickness, into u infinity. So, we will write this. So, we will get tau w by rho is equal to d by dx of u infinity squared theta plus delta star u infinity du infinity by dx, and this equation is what we call the final form of momentum integral equation, or after Karman, who derived this equation, it is also known as Karman integral equation. Karman was a PhD student of Prandtl who derived boundary layer. Now, this is an ordinary differential equation, and this equation is a function of delta, boundary layer thickness, which comes from theta and delta star. We have written this in terms of 0 to infinity, but if you remember, we said that this can be approximated delta star integral 0 to delta 1 minus u by u infinity dy, and similarly for theta the limit will be 0 to delta, because beyond delta to infinity u is equal to u infinity, and this term becomes close to 0. So, this has implicitly delta into it, there is tau w, there is u infinity, and both delta star and u infinity are function of u by u infinity, which is basically the profile of velocity in the boundary layer. So, to solve this equation, let us say if we want to find out the variation of boundary layer thickness along the x direction, we can use this equation, or for a known delta x we can find out tau w. Now, if we want to find out delta x, we need to know first u infinity, which is easier because u infinity is the velocity in the outer region. So, we can use potential flow solution to find what is the variation of u infinity with x. Now, we also need the velocity profile. So, as we discussed earlier that u by u infinity is self similar solution. So, the value of u by u infinity in terms of y by delta will be same across all the x. So, we need the velocity profile u by u infinity as a function of y by delta. And we also need tau w, but when we know the velocity profile, we can find tau w, because tau w is nothing but mu dou u by dou y at y is equal to 0. So, once we know the velocity profile, we can also find out tau w. Okay. So, we can make an assumption about the velocity profile, if that see that how we can find the profile of boundary layer. So, what we are going to consider now an example and see how we can use the momentum integral equation to solve or to find out the different parameters of boundary layer, for example, the boundary layer thickness. So, we will consider a case of laminar flow over a flat plate. So, when we have a flat plate, the velocity is coming and the flow is uniform. So, u infinity is constant across the y, and we will have u infinity not a function of x, and pressure gradient there will be 0. So, we will have a 0 pressure gradient along the x direction as well as 0 gradient in the free stream velocity along the x direction. That is valid for a flow over a flat plate. So, it might be a laminar or turbulent, but what we are going to consider is laminar flow over a flat plate, because we need to make an assumption about the velocity profile. So, let us assume that the velocity profile is parabolic here, but before we do that, we can write down this momentum integral equation and see that the second term here, which has du infinity by dx is 0. because we have considered the flow over a flat plate. So, in many books you might see only this form of momentum integral equation, because in that they consider the flow over a flat plate. So, this term becomes 0. So, for a flat plate you will have a simplified form of momentum integral, which is tau w by rho is equal to d by dx of u infinity square theta. Now, as I said, we can assume that the velocity profile is parabolic. So, we can assume a quadratic equation here, where we have 3 constants a, b and c. Now, we can find these constants that at y is equal to 0, which is at the wall, u is equal to 0. We have written this in non-dimensional form. So, u by u infinity is equal to a y by delta squared plus b y by delta plus c. We have 3 constants here a, b and c. So, we have first boundary condition, no slip boundary condition on the wall. The next boundary condition is at y by delta is equal to 1, which is the surface at the boundary. At the boundary layer, at y by delta is equal to 1, you will have u is equal to u infinity, or u by u infinity is equal to 1, and the gradient of velocity here will be 0. So, we can also say that d by dy of u by u infinity is equal to 0 at y by delta is equal to 1. Okay. So, when we do that, so from this first boundary condition, that y by delta is equal to 0, at that location u by u infinity is 0. So, when we substitute that, we will get u by infinity, which is 0, and this term will be 0 because y is equal to 0. The second term will also be 0, and we will have c is equal to 0. Now, the next boundary condition, that at y by delta is equal to 1, which is at the boundary layer interface, u by u infinity is equal to 1. So, we can write this u by infinity is equal to 1, y by delta is equal to 1. So, that gives us a plus b is equal to 1. The next is at y by delta is equal to 1, the differential of u by u infinity is equal to 0. So, we can differentiate this with respect to y, and that will give us 2 into y by delta, or a by delta squared. So, we can write this d by dy of u by u infinity, that will be 2 a y by delta squared plus b by delta. So, when we have y is equal to delta, then we will get from here this is equal to 0. So, this becomes 0, and 2 a over delta plus b over delta is equal to 0, or we can simply write 2 a plus b is equal to 0. Now, when we simplify, or from this we can say that b is equal to minus 2 a, and we can substitute in this equation. So, we will get 1 is equal to a minus 2 a, or minus a is equal to 1, or a is equal to minus 1, and b is equal to minus 2 a. So, b is equal to 2. So, that will give us, our equation will become, when we substitute the values of a, b, c in this, the equation becomes u by u infinity is equal to 2 y by delta minus y by delta squared. So, if we assumed a parabolic or quadratic velocity profile, we using the boundary conditions, we get this velocity profile. Now, from this we can also find out the shear stress on the wall, which is mu into dou u by dou y at y is equal to 0. So, when we do that, dou u by dou y will be, so we can write this u is equal to u infinity into 2 y by delta minus y squared by delta squared, and dou u by dou y is equal to u infinity into 2 by delta minus 2 y by delta squared. Remember that delta and delta squared and u infinity are not function of y. So, we can treat them as constants here. So, when we substitute that y is equal to 0, then this will be 0 when y is equal to 0, this term will be 0. So, you will have mu multiplied by dou u by dou y at y is equal to 0, which is 2 u infinity by delta. So, you will have tau w is equal to 2 mu u infinity by delta. Now, we can substitute the value of tau w there in the momentum integral equation. So, we have the value of tau w, and what we need is the value of theta. U infinity is a constant here in this case, and so we can write down the expression for theta, which is integral 0 to delta u by u infinity into 1 minus u y infinity dy. Now, just to remind again that we use the limit delta or infinity interchangeably, because at when the fluid is, or when we are in the outer region, u is equal to u infinity. So, this term 1 minus u y u infinity is 0. So, we can use either limit delta or infinity here. Okay. So, that is the definition, and we can substitute the values of u by u infinity in this equation. So, u by infinity is 2 y by delta minus y by delta squared, and 1 minus u by infinity will be 1 minus 2 y by delta plus y squared by delta squared into dy. So, we need to simplify it. We can multiply the terms. So, we can multiply this with 1 first. So, when you multiply 1 with, so you get 2 y by delta minus y squared by delta squared. Then you can multiply 2 y by delta with the negative sign in the first bracket. So, that will give you minus 4 y by delta squared plus 2 y by delta raised to the power 3. And finally, we can multiply the last term or third term in this second bracket with the terms in the first bracket. So, we will get plus 2 y by delta cube, and the last term will be minus y by delta raised to the power 4. So, we can combine the terms here. We have 2 y by delta raised to the power 2, and 2 terms we have with y by delta raised to the power 3. So, that will give us integral 0 to delta 2 y by delta minus these two terms. When you combine, this will become minus 5 y by delta squared. These two terms, when you combine, this will become 4 y by delta cube minus y by delta raised to the power 4. So, that is your theta, and when you integrate it, so you will get the after the integration. So, you will get you are integrating with respect to y. So, 2 delta into 1 by 2 y by delta squared and so on, and when you simplify this further and doing a bit of algebra, you will get value of theta is equal to 2 by 15 delta. Okay. So, we have theta in terms of 2 by 15 delta. So, remember we talked about that you can use the momentum integral equation to find out the boundary layer thickness here. So, we can replace now theta in terms of boundary layer thickness. So, we will do that, that theta is equal to 2 by 15 delta, and we also have tau w, which is 2 mu u infinity by delta. So, we will have this equation simplified because u infinity squared into 2 by 15 is constant. So, we can bring this out here, rho has come on the other side. So, we can write tau w is equal to 2 by 15 rho u infinity squared d delta by dx. Now, we will have that, remember this delta is a function of x. So, we can combine the terms or separate the variables each side and can try to integrate it. So, we can combine this term delta into d delta one side, and this 2 and 2 will cancel out, and we will have 1 u infinity also cancelling out. So, 15 into mu, this term and this term we have taken care, and divided by rho u infinity into dx. So, that is our equation. We can integrate it. So, that will be delta squared by 2 15 mu by rho u infinity into x plus a constant. Now, to get this constant, when we have a flow or a flat plate at x is equal to 0 at the leading edge, the velocity or the boundary layer thickness will be 0 at, so delta is equal to 0 at x equal to 0. So, when we substitute, we will get this constant to be 0, and we can rearrange this. So, we will get delta squared is equal to 30 mu x by rho u infinity. Now, we have rho u infinity here. So, we can multiply x at the denominator and numerator. So, we will get square root of 30 multiplied by square root of x square, which is x, and this term here is basically 1 over r e x. So, we get delta is equal to x into root 30 divided by square root of r e x, or root 30 is 5.48. So, 5.48 x in divided by root r e x. So, delta by x is equal to 5.48 divided by square root of r e x. And we discussed in the previous class that this number is comes out to be 4.91 from an exact analytical solution. So, we are not too far off, and the assumption that we made here is that the velocity profile in the boundary layer is parabolic. Okay. So, if you can make an educated guess about the profile in the boundary layer, you can use this methodology to find what is the boundary layer thickness as a function of x. Now, we have found the boundary layer thickness, we can also use this to find tau w. So, we will do that to find tau w, or we define a non-dimensional parameter which is called skin friction coefficient. So, that is defined as Cf, it is represented by the symbol Cf, and it is defined as tau w non-dimensionalized by dynamic pressure in the free stream half rho u infinity squared. So, that is called as skin friction coefficient. So, skin friction coefficient will be tau w, which is 2 mu u infinity by delta divided by half rho u infinity squared. 1 u infinity will cancel, and you will have 2 by 2 into 2 multiplied. So, you will have 4 mu divided by u infinity rho into delta. Now, delta is a function of x. So, Cf is also going to be a function of x. We can rearrange this a bit, and so we can write that delta is 5.48 x divided by root r e x. So, that is our 1 over delta, and this multiplied by mu into u infinity into rho, and this x probably is extra here. So, we will have this, so we can remove one of those x's. So, u infinity rho into x. So, you will have 4 divided by 5.48, that will give you 0.73, and root r e x divided by this number again will be Rex. So, mu divided by u infinity rho into x, that will be 0.73 divided by root Rex. So, that is the value of Cf. Okay. So, we get this skin friction coefficient as a function of x here. So, we have found the value of delta as a function of x, which is 5.48 x divided by square root of Rex. We also calculated Cf here, which is 0.73 divided by root of Rex. Okay. So, when we integrate this Cfx or tau w over the flat plate, then we can obtain the total drag on the flat plate. So, in summary, what we have done today is we did a lot of substitution, integration, differentiation, but what we got or what we did today is derived a momentum integral equation. So, we considered a steady 2-dimensional incompressible boundary layer in Cartesian coordinate. We applied the momentum balance equation, and when we applied momentum balance equation, we needed a term m dot b c, which was the mass flow rate that is going out of this control volume, or m dot b c. Then we used a mass balance equation to find that mass balance and obtained a equation for integral momentum balance. And that was the equation which was rearranged so that we get in this nice form, which is a function of theta momentum thickness and delta star displacement thickness. So, this also tells us the importance of these two thicknesses, theta and delta star. Probably the definitions comes because this equation was derived, and these equations, the ones we saw the mathematical form of it and the physical significance of these terms, then they were defined the way they are defined nowadays. And then we considered this equation to solve the laminar flow over a flat plate. We needed, of course, u infinity, we needed theta, and we needed tau w to find delta. So, theta or because this term will become 0 over a flat plate, the pressure gradient is 0, and gradient of free stream du infinity by dx is also 0. So, we needed tau w and we needed theta. For theta, we needed the velocity profile. So, we assumed a velocity profile. Remember, this was an assumption, it is not necessarily comes on from a physical basis. We assumed that it is a parabolic velocity profile, and then we used the boundary condition to obtain the constants in that. Once we obtained the constants, so we could get a velocity profile, and from this velocity profile we could also calculate tau w, which is mu multiplied by du by dy at y is equal to 0, and using the velocity profile we also could obtain theta in terms of both tau w and theta in terms of delta. Once we obtained that, we substituted and obtained a differential equation for delta and integrated it and obtained the value of delta. From that, we also calculated skin friction coefficient, which is basically non-dimensional form of shear stress tau w by half rho u infinity squared. Okay. So, we will stop here. Thank you.